All right, we'll get going here. So I handed back the exams. There's obviously no scores on them. It's just the Scantron. So I have the scores and kind of what each answer was in an Excel file. So they weren't the best, but usually this exam is the lowest average of the three. It wasn't too far off of where it sometimes is, although I have like a lot of unofficial drops. So the zeros were pulling it down a little bit. So what I'm going to do is and don't have to tell you guys because you're all here today, but for anyone listening to the recording, I can't emphasize enough how for this last month, like you should really try to show up to class. I can see a pretty strong correlation between the people that and the names I recognize for people that are here and the performance on the exam. And I crossed my three sections. I've got varying levels of people showing up, and the section that did the best is you guys, and you always kind of have the most people showing up. So you're doing the best, but if you're not here I'm talking to you, start showing up. Otherwise, I don't think this stuff is going to sink in. I think just kind of seeing it, actually having to focus. I can just speak it for myself, but if I'm listening to a YouTube video of someone talking about something, my mind can wander very easily, right? It's a lot harder to kind of focus. I mean, you can wander here, but at least you can ask questions. Just having the opportunity to ask a question keeps you a little bit more engaged. And so I strongly suggest everyone trying to attend as much as possible. That being said, you guys are here today, get the added bonus of getting a little bit of an extra head start. Also, maybe even just being aware, because if people don't watch this video until, I don't know, next week, they won't be aware of this. I'm going to let you do corrections to earn some of the points back. So they're not scored, right? I will be uploading the grades at some point over the weekend. I just want to be, it might even be today. I just want to be a little bit more confident in having everything kind of ready to go. But I'll get the answer keys up there as well as the exams so that you can go through and figure out which numbers you got wrong. Then once I upload your score, you'll be aware of how many you got wrong, and you can make sure that you've gotten every single one, right? So once those grades are up there, it'll be easier to identify how many problems you got wrong, but you still need to figure out which ones you got wrong. So you still have to go through the process of looking at the answer key, figuring out which ones you got wrong. And then if you rework the ones you got incorrect, I haven't decided on the number yet, which is I didn't kind of hand these back today, but I wanted those people who showed up after the exam today to get a little bit of an extra bonus, like head start on things. So it's going to be somewhere probably between like 0.3 and 0.5 of the points back. But let's just assume that I end up giving you half of the points back that you missed. Basically, if I got 10 wrong, right, that would be a total of 50 points, right? So I'd have a 50. But of those 50 points I missed, if I rework each one of those questions, and I'll post an announcement on Canvas, it's a little more specific. When I say rework, that does not mean tell me the answer is C. That means work out the problem, show me all of your work, and arrive at the correct answer. Right? That is what reworking the problem means. Okay. So rework the problem, show me all of your work to get to the correct answer. Right. You only have 3 left, right? Because you got it wrong, so you know which one isn't right. And then if you turn those in, I would give you, like I said, at most half the points back. So half the points, you could go from a 50 all the way up to a 75. Right? Like I said, I don't know if I'll quite get back half of the points because that's a pretty large kind of shift there. But even if it was 0.3, that's still, right, a pretty significant portion of those points back. You can really boost your grade if you didn't perform so well, right? And then I'll get a link up on Canvas over the week. I don't know. I might not do it till Monday. We'll see if I get to. I'll probably forget to do it on the weekend. But I'll get a link up where you can upload your work or your answers. You can also turn in a physical copy in class anytime next week. But just so you don't have to turn it, it's going to be due at the end of the day Friday. So if you didn't turn it in class, I don't suggest waiting until Friday to work on it. But just if you did, I'll have that Canvas, what looks like an assignment, where you can just upload your kind of your corrections there. I'll probably call it exam 2 corrections. Any questions on that? Like I said, I'll get all this up on Canvas. I just didn't have a whole lot of time to think about it. I didn't get these back until kind of later in the day yesterday. But looking at the scores, I do want to kind of give some of those points back. I just have to figure out exactly what percentage. But those of you who are here today, you can kind of get an early start on it, start working on those so you can get kind of boost your grade. Okay. Okay with that? All right. So we left off talking about hypothesis testing, right? And we're doing p-values. We're doing the p-value approach to determine, can we reject the null hypothesis or not? So we have these left, right, and two-tailed tests, right? And the example that we'll specifically work through today, later on, will be a proportion example, but it doesn't matter. We could do this critical value approach for proportions or for a sample mean where we know the population variance, right? Both situations, we should be using that standard normal distribution, okay? So the steps will be very similar to the p-value approach initially. I'm going to determine the null and alternative hypothesis. I'll have some alpha where I can test against all three of our benchmark alpha values. Using alpha now, so usually we would calculate our test statistic and then find a p-value. Now we're going to calculate our test statistic, but we're going to use alpha to find what we're going to call critical values. Okay. So instead of finding a p-value, we're going to use our alpha to find the critical values. And then instead of comparing our p-value to alpha, we'll compare our critical values to our test statistics. In this case, z statistics, since we're working with the examples where we are using that z table or the standard normal distribution. Okay. So those are going to be kind of our 5 steps. And we'll I'll flash these back up here later on, but this is just kind of to show it's going to be a little bit different than p-values. Okay? So we're going to come up with this critical value, which is a threshold z value, right? So what I'm saying is, look, if I see something that's, let's say I set my threshold z value, this critical value at 2. What I'm really saying is, if I see sample evidence that has a test statistic greater than 2, right? Which would mean, right, my test statistic is a z value, it's a z statistic. So if I see sample evidence that is more than 2 standard deviations away from this assumed true mean, I'm okay rejecting it, right? So we're, instead of setting like this threshold alpha or this threshold probability, and then say, okay, does the probability fall below this? We're now going to set a threshold z value and say, does our test statistic fall above this, right? Or is it even further number of standard deviations away? So what this is going to look like is something like this. So I think I'm going to do left-tailed test first. So let's say I'm looking at the distribution of sample means. I've got this assumed true population mean, and we're going to be looking at a left-tailed test. So we've assumed that it's less than a certain value. No, sorry, we didn't assume that. We want to find if it's less than a certain value, so we assume that it's greater than or equal to that. Okay. So we've got a left-tailed test. Usually, what we would do is we're going to see some sample evidence. If it was inconsistent with the null or supports the alternative, that would be something that is below that assumed true mean. We would then look up the area to the left, and that would be our p-value. Right? Well, how did we find that? Well, we usually turn this into a test statistic and then found the area to the left. Right? We're not going to do that now. What we're now going to do is say, okay, look, I've got my standard normal distribution, and I know that I can find a z value, or this cutoff, this critical value, that would correspond to having whatever my type 1 errors that I've set are, right? So let's say alpha is 0.1. That's my, remember, our probability of making a type 1 error. I can find the z value, or the number of standard deviations away from that assumed true mean, that corresponds to that area of 0.1 being in my left tail. Once I find that critical value, or that threshold z value, that's all critical value is. It's a z value, but it's like a threshold z value. If I see something a higher number of standard deviations away than whatever this threshold is, then I'm okay rejecting. So I draw like this arrow to kind of visually represent, here's my rejection region. Okay. So if I wanted to do this, how would I look up this critical value? Well, I know the area that I want in the tail, which is alpha. So I'm basically working in reverse, right? Or I'm doing the inverse process. So I'll go to my Z tables. I know that I wanted 0.1 in that lower left tail. So I'm going to go over here. Looks like I'm in between these two values. So negative 1.28 and negative 1.29. I'll use the higher of the two. So we're just using this skill that we already had, which is to, once I know the probability or I know the area in the tail, I can find the corresponding Z value. It's just now that Z value represents my critical value. So all critical, like my critical values here are Z values. We just call them a different name because they represent a threshold Z value. Right? That might be a better name for them. It's a threshold Z value. Okay. Well, now, if my sample evidence corresponds to a test statistic, right, or a Z statistic, comes from a Z table or standard normal distribution, if that Z statistic falls in the rejection region, I'm okay rejecting. Right? Now, mathematically, like I think the visual, like the p-value approach to me is easier, but the visuals on the critical value approach, I think make it, if you're a visual person, like really makes it easier, right? I've got my rejection region, I plot my test statistic. If it's in that region, I reject, right? That's a really nice visual. But mathematically, what we're really saying there is if that test statistic or my Z statistic here, if it's less than my critical value, right? Because I'm dealing with negative values on the left side of this standard normal distribution. So I'm actually saying if that test statistic is a greater negative value, which would really be less than. Any questions on that? Okay. Now, one thing that we'll kind of end up using is it's going to kind of get tricky, like left tail test, I'm saying is it less than. We're also going to have right tail tests, which are going to be is the test statistic greater than. So one way we can kind of resolve this issue, I'll just kind of jump ahead, is no matter what type of tail test I have, if I'm looking for my rejection decision, if I take the absolute value, so that's what these like two bars on either side, if I take the absolute value of my critical value and the absolute value of my test statistic, then it's always going to just be, is the absolute value of the test statistic greater than the absolute value of the critical value? Well, all that's really saying is, does my test statistic represent being a higher number or a further number of standard deviations away from the assumed true mean than this threshold amount that I set? And that way, it doesn't matter if it's negative, doesn't matter if it's positive, that will always kind of work. If that holds, we'll reject, right? So here, if I took the absolute value, like this was like, I don't know, negative 1.9 or something. Or if I drop the negative signs, I would have 1.9 and 1.29. Sure enough, it's going to be greater than, so I'm okay rejecting. Okay, but I don't know. This gets a little mathy, and so I don't think everyone is maybe as math inclined or likes math as much, and so I think having the visual often makes this critical value approach quite a bit easier. Okay. Any questions before I move on from this? Got everything jotted down? Okay. So the other type of tail test we could have is not a left tail test, but instead a right tail test. So it's going to be very similar in how we would look up critical value. So think about for a right tail test, right? We're assuming that it's greater than a certain value, or we're not assuming, sorry, we want to test for whether or not it's greater than a certain value and assuming the opposite is true. So we've got a right tail test here. So now evidence, on the right would go against that null. So if I'm thinking about my standard normal distribution, right? Maybe I want to find the critical value that corresponds to having that same alpha that I was using for my left tail test of 0.1, right? So what Z value would give me 0.1 in the upper right tail? Well, there's a couple ways to find this. I could look up 0.1, right? But that would be the area in the left, right? The table always looks at the area to the left. So what I would really need to look up is, the area in that left tail is actually 0.9. Right? So I'm going to go to my standard normal table, scroll down a lot to find 0.9. Looks like I'm in between these two values. So 1.28 and 1.29. So here we just found this was 1.29. Now, if I had looked up 0.1, notice I'd actually be looking at 0.1 in the lower left tail. That z value would be negative 1.29. But if there's 0.1 to the left of negative 1.29, and it's a symmetric distribution, should give me 0.1 to the right of positive 1.29. So if I just want to look up alpha and then remember, well, for a right-tailed test, what's going to be true about my critical values? Remember, the mean of my z, or my standard normal distribution, is 0. So the area to the right of that is 0.5. So if I'm looking for the area of like 0.1 or 0.05 or 0.01, all my critical values are going to be positive. Right? So I can look up alpha. It'll give me that z value, but I'll just remember, oh yeah, that's the left side of the distribution. I'm dealing with the right. So it's going to be that same value, but positive, right? So for our left and our right tail test, we're finding the same values. It's just for our left tail test, our critical values are going to be what? Yeah, all negative. So if we think about for our left tail test, critical values are negative. For our right tail test, critical values are positive. And once we have that critical value, now our rejection region for a right tail test is the area to the right. So I could say, okay, where does this fall? Well, in this case, I see actually my sample evidence wasn't 1.29 standard deviations or further from that assumed mean. It was something a little bit less. So this would be a scenario where I actually fail to reject the null. Right? That sample mean corresponded to a test statistic that wasn't quite in the rejection region. Okay. Questions on that? So what's the other type of tail test that we have? Yeah, so we can do critical values for a two-tailed test as well. I'm trying to keep these different colors because I'm going to start throwing them back up here occasionally. So let's say I've got a two-tailed test. Start out. And you don't necessarily have to always draw out the distribution of your sample means. I'm just doing it to kind of hopefully help make, hopefully this makes a little more sense. And trying to be real complete about it. But as we start working through more problems, I'll probably stop drawing this as much. So here, maybe I see sample mean out here and thinking about my critical values, right? Well, now evidence on either side of my null hypothesis could go against it, right? So it doesn't matter if I'm 1.6 or 1.29 standard deviations above or 1.29 standard deviations below. That still goes against it. So I'm actually going to need two critical values. They're basically going to be the same value. One's positive, one's negative, right? Because what I'm really saying is if I see sample evidence that's more than 1.29 standard deviations above or below, then I'm okay rejecting. So now my rejection region, I'm actually going to have kind of like two rejection regions, right? One to the left of the negative critical value, one to the right of the positive critical value. Okay? Now, the way I have it drawn, it looks like the sample means in that rejection region, but I don't really know until I calculate my numbers and actually figure out what my critical value is and what my z statistic is in practice. So how am I going to find these critical values? Well, alpha is the total area in my tails. Okay? So just like the p-value, right? The total p-value is the area in both tails. Right? So if my alpha was 0.1, what would I have in each tail? Alpha over 2. So 0.1 over 2 or 0.05. So I've got to divide alpha by 2 and figure out how much, what area is in each tail, right? And then based off of that, what critical value would correspond to having that alpha over 2 in each tail. So that looks very similar to confidence intervals. It's almost exactly what we did with confidence intervals. And once we start working through some more examples, I'll kind of connect the confidence intervals to the hypothesis testing. When it's a two-tailed test, basically any value outside of our confidence interval, we would reject. And any value within, we would fail to reject. Right? But with the one-tailed test, there is a little bit of inconsistency there, but yeah, very similar to confidence intervals. So I'll go to my table, 0.05. Sorry, 0.05 is the area that I want in my tail. So really close to these two. So negative 1.64 and negative 1.65. So we've got, found that critical value there. Oh, but I also have another critical value. So if I'm 1.65 standard deviations or more above, or 1.65 standard deviations below or further below, those are going to be the values for which I'll reject the null. Right? So I'm now going to have a pair of critical values. Any alpha for a two-tailed test, and I'll usually write this out like this, right? We've got a pair of critical values, one's positive, one's negative. Right? They're always going to be the same value though. Okay. Any questions on the two-tailed test before I keep moving here? Okay. All right. So got a little bit of a summary here. This is kind of also on this slide. I wouldn't get too lost in the formulas necessarily. Like all I'm really saying here was, you know, that depending on if it was a right or left tail test, that sign would change. But I kind of told you, if you actually just use this rejection decision for the two-tailed test, where you take the absolute value of both of those, that'll always lead to the right rejection decision as long as your sample evidence is inconsistent with the null. So if you've got sample evidence that's inconsistent with the null, you can simply take the absolute value of your critical value and the absolute value of your test statistic, just drop the sign. And if your test statistic is greater than that critical value, you can reject. And really that's because what you're saying is my sample evidence was a further number of standard deviations away than this threshold that I set. I also kind of have here, you know, notice for this for this right and left tail test, we're always going to find the same three values. Like for right now, we get used to like looking these values up, finding the critical value from that standard normal table. But if I'm looking up 0.1, 0.05, and 0.01 every single time, I'm going to keep finding the same three Z values. So by the time we get to the final, you may even just be like almost know these, right? Just because you'd be kind of familiar with them. So notice left and right tail test, same critical values, but negative for a left tail test, positive for a right tail test. Because alpha gets divided by 2, since we have two tails for that two-tail test, our critical values are going to be different values, right? And we're going to have pairs of critical values at each alpha. Okay? So we'll start seeing these numbers pop up a lot, right? Any questions before I keep moving here? I think the rest of what I have here is this stuff we've already really done. You know, once we calculate that test statistic, what we're really saying is this is the number of standard deviations away. Excuse me. So we can look up that test statistic. Excuse me. We can plot that test statistic against this critical value, which we find the critical values by. We know we want alpha, and you know, depends if it's a left, right, or two-tailed test. We want alpha in our tail or our tails if it's a two-tailed test. We can then find what Z value or how many standard deviations away would give me that desired alpha in the tail. Yeah. Like left, right, or two-tailed. So from an actual problem, right, I'm always going to be looking at that alternative hypothesis, right? If I had a not equal to sign in that alternative hypothesis, this is what we said was a two-tailed test, right? Because evidence on either side of this assumed true mean goes against the null. For that, if I have a greater than sign, this was our right tail test, right? So greater than or to the right is a right tail test, and then we had our less than sign of the alternative hypothesis, which was our left tail test. It would have to be like given to us. We'll work through a problem here where we will identify the null and alternative hypothesis and then kind of identify it from there. So that'll probably help give a little bit of clarity. All right. So is there anything else I wanted to say here? We talked about looking these up. This is just like a nice summary kind of visual slide where it reminds us that for a right tail test, our rejection region is this area to the right, left tail test, area to the left. Two-tail test, I've actually got like two rejection regions, one on each side. It also reminds me that these critical values, they're just threshold Z values, right? They're coming from that standard normal distribution. We kind of did all of this just slowly and a little bit more meticulously. So we've got our steps. We can work through an example here in just a second. But before we do that, I think I want to try to connect these equations, connect these two approaches. Okay? So the p-value and the critical value approach. Why do we have two approaches, and why will they always lead to the same decisions? Okay? So if I think about what I'm doing with the p-value, I think I'm going to do the right-tailed test just to make it a little bit easier dealing with positive values. Right? When I see my sample mean, it's going to be a certain number of standard deviations away from that assumed true mean, right? Once I know how many standard deviations away that it is, well, that really just represents a z-value. That's the literal definition of my z-value. But because I've calculated this using an assumed true mean, we said we'll call this a test statistic or a z statistic, right? As opposed to just a z-value. So using that, I can then find the probability that I saw sample evidence that was this many standard deviations away from the assumed true mean or anything even further, right? That's what that p-value represented. That was the probability I saw this z statistic or sample evidence this many standard deviations away or something even further. So you can kind of think about my test statistic has a corresponding p-value, right? So I'm just using a subscript there to kind of remind us of that. And I think we'll see why in just a second. What I'm then doing with my critical values, I'm saying, look, this is the critical value that gives me alpha in this tail, right? So our critical values are just z-values as well. So when I compare my p-value to alpha, we said we reject if that p-value is less than alpha, right? So my p-value is less than alpha, the total area I wanted to tail there, so I could reject. I'm comparing probabilities. The probability that I saw sample evidence as inconsistent with what I assume to be true or something even more inconsistent to the probability that I make a type 1 error. I'm just comparing those probabilities. When I use the critical value approach, I'm just comparing the number of standard deviations away, right? So the number of standard deviations away my sample evidence was, my threshold number of standard deviations away, right? Or my threshold z-value. So it's really like I'm just comparing two sides of the same coin, right? I'm comparing either the probability of seeing something that's that many standard deviations away, or I'm just comparing these number of standard deviations away, threshold that I set, and the number of standard deviations away my sample evidence was. Okay? So, if I look here, if my p-value becomes anything less than alpha, automatically what has to be true about my test statistic is it has to start to be larger than my critical value, which is exactly what we had for our rejection decision with the critical value approach. Right? So those two things kind of go hand in hand. Right? You can kind of think about it this way. This isn't perfect, but it's a different way of thinking about it. I'm trying to make it kind of large here. So if I think about like a function that's going like this, which really, right, as I move to a higher test statistic, that area in the tail or the probability is getting smaller. So I have like this inverse relationship. So if you told me that, what do I want here? I want to make sure. Kind of think about just some general function, and we'll put kind of our probabilities or the area in the tail up here, and then that z-value that we're looking at. If you tell me that z1 is less than z2, I automatically know that my probability for 2 is going to be less than my probability for 1. Right? So anytime my test statistic is getting larger, automatically I know that that probability or that area in the tail is getting smaller. Right? So that's why it doesn't matter which we compare. This will always, kind of lead us to the same rejection decisions. And if this doesn't make a lot of sense, don't worry too much about this. If you're mathematically minded, this might have helped clarify a few things. Any questions before we jump into a problem here? Okay, so let's take a look at this one, and I'm going to change it a little bit. I wanted to kind of show an example. Well, I'll hold off on explaining. So let's just start jumping to the problem, and then I might change something for us, okay? So let's say you want to test the hypothesis for whether or not the true proportion of people who own a gun is 50%. Right? So remember, what we're testing for is always our alternative hypothesis. Right? So we're saying, is that proportion, we want to see, is it greater than 0.5, right? 50% probability of 0.5. So I'll assume the opposite is true. So what type of tail test do I have here? I got a greater than sign. So I've got a right-tailed test. So automatically, we'll come back to the sample in a second. So we got a right-tailed test. Automatically, what has to be true about my critical values here? Yeah, if they're coming from the right side of that distribution, they're all going to be positive. I can rule out B and D here right away. Now, from there, how do I find these critical values? Well, what I really would like is to look up the critical value that would be associated with an alpha of 0.1, the critical value that would be associated with an alpha of 0.05, and a critical value associated with having 0.01 in the upper right tail. Once I find those, my rejection regions are going to be the area to the right. So how do I find these? Well, if I want 0.1 in this upper right tail, when I go to the table, I actually have to look up 0.9, right? The area to the left. Now I could go through and look up each one of these, right? I could just look up alpha and then remember, oh yeah, it's going to be all those values, but it's a right tail test, so positive. So we could do that. It's kind of cumbersome a little bit, you know, like if I go to my table, I'll look up 0.01 first. So where's 0.01? It's in between these two. So negative 2.32 and negative 2.33. Okay, so 2.33, negative 2.33, but I'm got a right tail test. So it's that same value, but positive, right? If there's 0.01 to the left of negative 2.33, there's 0.01 to the right of positive 2.33. I then keep going. I got to look up 0.05 next. In between these two, negative 1.64, negative 1.65. So positive 1.65 for the right tail test. And then I'll look up 0.1. That was the last alpha value that we were going to look up in between these two values. So negative 1.28 and negative 1.29. We'll take the higher of the two, negative 1.29. But we're dealing with a right-tailed test, so that value but positive. Okay. So we could look up our three critical values like that. Okay. Or there's a nice shortcut, right? So before I do the shortcut, are we okay with this? So right, all I'm doing there to look up critical values is basically using that Z table, but using the inverse process. I know the areas that I want in my tail. Now I wanted three of them. I'm looking up three different values. So 0.1, 0.05, and 0.01. Well, if I know the area in the tail, that's those probabilities that are in the middle. Now for a right tail test, I should be looking up the area to the left on that table. But kind of what I said is you could just look up alpha because you know this is a symmetric distribution. The left and right tailed critical values are always going to be the same. It's just that for the right tail test will be those values but positive. So I would just say look up alpha and then remember, okay, if it's a left tail test, my critical values will be these values, the negative values. If it's a right tail test, same values but positive. Any questions on that? I feel like there are. Yeah.
So if there's like, so if we figured out that there was a test statistic of like 0.4, then we would fail. Then we would reject for the 0.1.
Yep, because it'd be right here. We'll go through one, and I'll give you a little bit more insight into that as well. Any other questions from the one? Okay. So we'll go back here because I'm going to change the example from the slides just a little bit. So we've got our critical values, so that's good. But I'm going to change this. Okay, if I saw, and it doesn't matter, like I can draw this below. I'm just like drawing it to have a reference. If I saw sample, what did I assume? And then we're doing a proportion example. I assume that it's what? That population proportion is 0.5, right? That value from my null and alternative hypothesis. If I see a sample proportion of 0.41, it's going to be over here. What's going to be my rejection decision? It's pretty easy. So remember, our null alternative hypothesis were right here. So I had a right-tailed test. So I found evidence that actually supported the null. So I don't even have to go through the steps. I know that I'm going to fail to reject, right? Because I need to see something 1.29 standard deviations above in order to reject it. I saw something that was below, so of course I won't be anywhere close to that rejection region. So we're going to choose one that's a little bit more interesting, which is, what if I saw a sample proportion of 0.59? Okay. So if I see a sample proportion of 0.59, where, if I turn that into a test statistic, where would that fall in relationship to my critical values? Right? So I don't know, right, until I actually calculate it. So we'll keep going over here. And I tried to be pretty friendly on the exam. And even in this setup example, like even when I tell you the sample proportion is this, I also gave you the notation of p hat is equal to this. Right? So that way you've got 3 test statistic equations. Well, you can match up like, oh, I've got a sample proportion, I've got p hat. I need to use that test statistic equation for p hat, for my sample proportion. Okay. Well, my sample proportion we found was 0.59. The assumed true proportion, 0.5. And then that sample size is 100. I think it was 100. Is it? Yeah, okay. So then, oops, we just basically plug those values in and determine what our test is. So this step, there's not a lot of insight I can give, like other than matching up the equations to the type of example that we have. From there, it's just plugging their values in. Okay. So 1.8, so this goes back to your question. Where would 1.8 fall here? If I'm plotting that, it's going to be what, like right here? So I plot my test statistic of 1.8 against my critical values, and I can see, let's see here. Keep all this on the same thing. So I can see here that if I wanted to make my rejection decision, the visual is really nice and easy, right? I'm in the rejection region when alpha is 0.1. So when alpha is 0.1, we said my significance level would be 10%, right? So I'm in the rejection region at the 10% level, so I can reject. At an alpha of 0.05 or a significance level of 5%, right? Am I in that rejection region? Well, not by much, but I am. So I can reject with 5% significance. What about when alpha is 0.01 or the 1% significance level? I'm not quite in that rejection region, right? I'm kind of further from that. So I could reject at the 10 and 5% significance level or with 90 and 95% confidence. But I failed to, reject at that 1% significance level, right? Because I wasn't quite in that rejection region. So I failed to reject the 1% significance, or I can't reject this with 99%. Let me focus over as I'm doing this because I want to try to keep this up here. Okay. Any questions on kind of that? Now, if I want to do the mathematical way, like I just did this visually after plotting those, but the same thing would kind of hold. The same thing would hold if I just compared the absolute value of my critical value and said, is it less than the absolute value of my test statistic? Notice, right, for 1.29, that would be less than my test statistic of 1.8. 1.65 would be less than my test statistic of 1.8. 2.33 would not be. Right? So all I'm doing there is using my 3 critical values, comparing them to my test statistic, this was the rejection decision. So we would come up with the same rejection decisions that we did, just kind of using the visual there. And that's why I said, I think the critical value approach for a lot of people is a lot easier because you have this really nice visual if you're drawing out what you're doing. Okay. Any questions on that? Yeah. Yep. So if you go back here, if we're looking for that test statistic, and ignore that slide because that was the original data, I want to change it to this new sample proportion. So all I do is plug in my sample proportion and my assumed true proportion and my sample size into this equation. Now, just as a reminder, what this is telling me, save this. So all I'm doing there really is I'm subtracting the mean of my sample proportions. So to calculate a z-value, we subtract the mean divided by the standard deviation. So I have to subtract the mean of the statistic I'm looking at, and then I'm dividing by the standard deviation of the statistic I'm looking at, which the equation that we had for that was the proportion times 1 minus the true population proportion, but I'm taking a sample, so over my sample size. So this is really, just telling me the z-value associated with the sample proportion I saw, or how many standard deviations away from this assumed true proportion my sample evidence was. But that is, that's where that 1.8 came from. The sample evidence we saw, that sample proportion of 0.59, what we're really saying is it corresponds to being 1.8 standard deviations away. Yep. Any other questions? All right. So let's say that I wanted to find I wanted to do the same question, but do you use the p-value approach? Okay. So my p-value would be the area to the right of my test statistic. Right? So if I look up this test statistic on the table always tells me the area to the left. Right? So if I look this up, it'll give me the area to the left. I want the area to the right, so it would be 1 minus that. Right? So I'll go ahead and I'll go to the table. I've now got my z-value. And I want to look up this, Yep. Yeah, so basically the z-table, that's a good way to say this. The z-table is really just matching up every z-value with the area to the left of it. So it's like if you wanted to, if you wanted to make it a table that wasn't usable in your hands, it might look a little bit easier to just write out every single z-value, and then right underneath it, you could write out, well, what's the probability I see that or anything below it. You would just have a really long, 2-row table where you could then see, okay, for every z-value, the probability I see that z-value or anything to the left is this value. It's just that to be able to have a table that's actually usable out to the second decimal, we would kind of organize it with these row and column headings. What, the p-values and things like that? Yeah, so I would say, so when it comes to z-values and critical values, a very good analogy would be z-values are like how fast your car can go, miles per hour. The critical value is the speed limit. It's a threshold, right? So you can see z-values, you could see speeds from 0 to however fast a car goes. And so we could see a z statistic or z-value anywhere in that range. And what we're doing with the critical values, we're setting a threshold, right? To say if z goes past this point, just like we set a speed limit to say if your speed goes past this point, you get a ticket. If our z-value goes past our threshold critical value, right, then we reject. It's like getting a ticket, reject it. I don't know. But that would be like the analogy of they're the same, a speed limit is a speed, right? It's just a threshold speed. Same idea. A critical value is a threshold z-value, but it still represents a z-value. Now the p-value, that represents the probability of seeing these certain z-values, right? So it's almost like you have this x and y axis, right? But they're related. It's just like if you told me, any two variables, if you have like a linear function, if you give me X, I can tell you Y. If you give me a Z value, I can tell you the probability of seeing that Z value. Does that help a little bit? Also, thanks for asking that question. I've never used that speed limit analogy, but it's really good. So, all right, so we've got our rejection decisions here, right? We can also do the p-value approach and see that we'll make the same decision. So let's say I want to look up that Z value of 1.8. All right, I keep going down here. So the area to the left of that Z value, that Z statistic of 1.8 is 0.9641. Well, if I know the area to the left, what I really wanted was the area to the right. So I would actually have to subtract that from 1. Right? So 0.9, or was it 0.9641? There we go. That was the area to the left of 1.8. I wanted the area to the right, so I needed to subtract it from 1. So there I'm going to end up with a p-value. It's about 0.0359. Okay. So that was just that area in the right tail up there, right? 1 minus the area to the left of that Z value of 1.8 that I looked up. So now when I'm making my rejection decision, remember is my p-value less than alpha? So is 0.0359 less than 0.1? Actually, I should probably do this in a different time, but is this less than 0.1? Yeah, right? So lo and behold, we make the same rejection decision that we did at the 10% level. Is it going to be less than 0.05? Yeah, so once again, I make the same rejection decision that I did with the critical value approach. Is it going to be less than 0.01? Not quite. Same decision I made with the critical value approach. So it doesn't matter which approach we use, we're going to keep coming up with the same conclusion. And that goes back to when I was showing you, this guy here, which was that anytime my p-value becomes smaller than alpha, I have to be looking at a test statistic that's larger than my critical value. And so I'll always be making the same rejection decisions, whether I use the critical value or the p-value approach. Okay. Any other questions over that example or anything else that we kind of talked about? So the reason I held off on this is because now we've got two approaches, right? You got even more things going on. But as we work through more of these examples, I think hopefully this will, just hearing it more often, hearing it said slightly different ways will help. So on Monday, we'll keep looking at these critical value examples, and then we might transition Monday, but for sure later in the week, we'll transition to looking at 2 population examples, right? So we're going to keep doing hypothesis testing, but it's going to give it a little bit trickier. Right? Might just say trickier. It has a little bit more, a few more parts in it, but the same principles are going to apply to those 2 population examples. So you should see that link for those corrections posted up on Canvas here in the next 15 minutes. I'll get the answer keys up as well as the actual exams, so you can figure out which ones you got wrong and rework them, right? Reworking them means what? Showing all the work, not just telling me the answer is C. That will not earn you back any points, okay? And I'll put up an announcement that specifies that and talk a little bit more about it on Monday, which I assume there might be a few people showing up to get their exams back. If you didn't get it at the beginning of the class, come up to me afterwards and get that, all right? So have a fun, safe weekend. I will see you guys on Monday.